Welcome everybody. Let's talk a little bit about vector spaces and in particular real vector spaces. Starting with a definition of what a vector space is, it really just consists of a pair of sets. We've got a set V that's going to be our set of vectors, and it's going to be a field F that consists of what we'll call scalars. Now along with those we have two operations. One operation where we define vector addition, and another operation where we define scalar multiplication. Now, in particular, these things have to satisfy some very nice properties that we want. And what those properties are, we want our addition operation to be commutative. We want our vector addition to be associative, and then we want it to have an identity element so that if we add 0 to anything, it doesn't change it. And finally, for every element that's in there, we want to be able to negate it, take it away, and so for every element is going to have an additive inverse. Now likewise, for those scalar multiplication, we want this to satisfy certain properties of those. So we've got a couple of distributive properties that says that if alpha times v plus w for a couple of vectors, that scalar is going to distribute across that vector addition. But then also our scalar multiplication also distributes across the scalar addition, so that alpha plus beta times v is going to be alpha v plus beta times v. And finally, we want a certain kind of associativity to go along with our scalar multiplication, so that alpha times the vector beta times v is really just the same thing as if we'd multiplied the scalars first, alpha times beta, and then done scalar multiplication and multiplied by v. And then finally, the last property that we really want it to have is that it does respect multiplication by 1. So if we multiply the scalar 1 times any vector, then that also doesn't change the vector. Okay, so the field F, we say that F could be this any field. That field could be any field. It could be, for our purposes, pretty much anything that will be the real numbers. Now it could be the complex numbers, it could be the rational numbers, it could be anything that really constitutes a field. And kind of if you want to look for all of the abstract algebraic properties that constitute a field, then you can go have a look at this link here. And that will take you to a Wikipedia page that will kind of give you a little bit of background about that. So let's go through some examples of what might be vector spaces. Well, our usual vector space with our n-dimensional real vector space, where we're just taking our usual vector addition, just done component-wise, and our usual scalar multiplication, where scaling a vector just means all of the components get multiplied by that scalar. So that's our usual example. Another example that we may have seen somewhere before is the set of continuous functions, continuous real-valued functions on the closed interval AB. So C of AB is just going to be this set. If we take any function that we're requiring to be continuous, it's just a function from the closed interval AB into the real numbers. Then the usual addition is just our usual addition of functions, that f plus g is actually defined as f of x plus g of x. And the scalar multiplication, alpha times x, is just alpha times the function evaluated at x. Maybe something slightly more exotic, and as an example of a rational vector field in this case, so now we're dealing with the field of rational numbers, is something that's called Q adjoin root 2. And so what that really is just all possible combinations a plus b times the square root of 2, where a and b are rational numbers. We define usual addition. We define our vector addition in that case as just a plus b times the square root of 2, c plus d times the square root of 2. We just essentially combine like terms with our square root of 2's and our just our rational numbers. And then the scalar multiplication, we just have kind of the distributive property. C times A plus B root 2 is just C times A plus C times B times the square root of 2. Now, when we've got these vector spaces, we really want to see that they behave kind of appropriately, or kind of how we think that they should behave. And so if V is going to be a vector space and C is any real number, then if we take 0 times any vector, that should give you the 0 vector. If we take any constant, any scalar times the 0 vector, we should still get the 0 vector. If C times V is going to be 0, then either that C is going to be 0 or V was going to be 0. And if we multiply -1 times a vector, well, that should behave in a way that just gives us the additive inverse of that vector. And so let's see why those things might hold. And so if we just start off with 0 times V, well, one property from the real numbers of 0 is that 0 plus 0 gives us 0. So then applying our distributive property, that just gives us 0 times V plus 0 times V. So then applying the additive inverse to both sides of that, we have 0. The 0 vector is going to be 0 times V plus negative 0V. And so we've got our 0V plus 0V plus the additive inverse of 0V. So then kind of using our associative and inverse properties, we can kind of rearrange those. So we've got 0 is equal to where we switch the parentheses, we group those together, but then we're using the inverse properties, and so that gives us 0, and then the identity property of adding on the 0 vector just gives us 0 times V. And so that gets us where we want to go, that multiplying a scalar times a vector, the 0 times any vector gives us the 0 vector. If we take any real number alpha and we multiply that times our 0 vector, well, we're kind of doing the same trick, that the 0 vector is really just 0 plus 0. Then using our distributive property, that's alpha times 0 plus alpha times 0. And so once again, using the associativity properties, the inverse properties, the identity properties, just gets us 0 is equal to alpha times 0. Okay, so that multiplying the 0 vector times anything doesn't change it from being the 0 vector. So now if we come down and suppose that a scalar times a vector happens to be 0. Well, if alpha was 0, then we've kind of already dealt with that in a previous case. We know that that's going to be 0. So let's suppose that that scalar is not 0. Well, this means that alpha is going to have a multiplicative inverse because we're dealing with a field. That's the nice part about having a field. We can have these multiplicative inverses. So that we've got 0 times 1 over alpha times 0. Well, we just proved that that was 0. And then that's equal to 1 over alpha times alpha v. But then kind of using our associative properties of the scalar multiplication, we can group our scalars together, but that's 1 over alpha times alpha. Well, that's 1. And we've already proven that 1 times v, or that one of our properties of being a vector space is that 1 times v is just going to be v. And so kind of ultimately putting all of this together, we've got 0 is equal to 0 times v. Well, 0 we can write as -1 plus 1. Use our distributive property. And so we have a -1 times v plus 1 times v. Well, that's -1 times v plus v. And so finally, because we have the additive inverse of v plus v is 0, then we've got the additive inverse plus v is equal to -1 times v plus v. Well, hit it with the associative property, the inverse property, the identity properties again, so that we can cancel out that v from both sides, and we get what we are actually aiming for. That scalar multiplication behaves as we think that it should. multiplying a vector by -1 actually gives us the additive inverse of that vector. So this kind of takes us through some of the beginning properties of vector spaces, showing us that they actually behave as they're supposed to. And so next time we'll pick it up with kind of more specific examples. I will see you guys later.